Acids and bases. So acids and bases are terms that you have grown up using a lot, but we're actually going to put proper chemistry terminology on them. So again, because chemistry is an experimental discipline, all of the stuff that we use to describe it has to be done in the lab first. So acids react with metals to form hydrogen gas. Sometimes they react very easily with metals. Sometimes they have to be coaxed. Either they have to be at a very high concentration or under high heat or both. But when they actually do react with the metals, they will create hydrogen gas. So you'll remember from your characteristic chemical reactions or your magnesium hydrochloric acid, you were always generating these fizzy bubbles from it, some very rapidly, some not so rapidly. Acids are also sour, not that you'll ever be testing that in the lab, but basically anything that is sour because it's acidic. And that's one of the things that you can add to something to make it sour. So Sour Patch Kids have an acidic citric acid that's often added to that. Excuse me. Acids also have a pH that is less than 7 at 25 degrees Celsius. It is temperature specific. And it turns litmus paper red. So I underlined the D in red and the D in acid. That's a little mnemonic if you need mnemonics. I always do. Bases, on the other hand, are bitter. So soap is a base. A lot of medicines are basic. All of those things have base compounds, or what we call alkali compounds to them, that make them bitter. They're also slippery. So again, soap is slippery. One of the reasons why soap is slippery is because it has a base in it. And the pH is greater than 7, again at 25 degrees Celsius, and it turns litmus paper blue. So the B in blue and the B in base. There are 3 definitions that we use for defining what an acid and a base are, and we're going to go over 2 of them today. So the Arrhenius definition of acids and bases is the most limiting. It requires the acid and base to be in water, and it defines them by what product they create. So acids will dissociate in water to create hydrogen ions, aqueous hydrogen ions. So here I have HCl dissociate in water to create the H plus ion plus, oh, by the way, the chloride ion as well. H2SO4 has 2 hydrogen ions that can dissociate, and H3PO4 has 3 hydrogen ions. So remember that when we talk about acids, one of the ways that we show that something is an acid is that the compound starts with an H. And the number of H's that are at the front will tell you how many protons can dissociate. So something that can only dissociate one proton is called monoprotic. So the prot refers to the proton. H plus, hydrogen that's lost its electron, is nothing but a proton. Diprotic means that it can create 2 hydrogen ions or 2 protons. And polyprotic is just something that can create more than 2. I could call it triprotic, but we usually just call it polyprotic. Arrhenius bases, however, dissociate in water to create the hydroxide ion. So I have lithium hydroxide creating the hydroxide ion here, and magnesium hydroxide creating 2 hydroxide ions. Oddly enough, and I verify this, we don't call anything like dihydroxidic or anything. We seem to only care about the acids. So again, Arrhenius acids and bases require water, and it's the dissociation, and we only discuss them in terms of whether they create a proton, as in acids, or whether they create a hydroxide ion in bases. We don't care about the other ion that comes in along with it. Bronstead-Lowry definition defines acids and bases in terms of a proton transfer. So unlike Arrhenius acids and bases, where I just have one thing that I'm dumping into water, Bronstead-Lowry looks at it and says, actually what's going on is that there's a transfer of a proton. So protons, like electrons, don't just sort of like hang around. It's not like you can pick one off the floor, that you found one somewhere. It requires a transfer. So something has to receive that proton if something is giving that up. So Bronstead-Lowry acids will donate protons, and Bronstead-Lowry bases will accept or receive those protons. Nothing floats around. That proton is always attached to something. So if I go back to the Arrhenius definition, really what I'm looking at is that this acid has donated its proton to this base. So HCl, when it dissociates, it's not just sort of letting go of its proton, it gave it to the water. And so I create the hydronium ion, or H3O plus, and I'm leaving alone my chloride ion. Notice that the total charge on this side is the same thing as the total charge on this side. I'm transferring an H and a plus charge. So the acid loses that H in the plus to become Cl minus, and the base gains that H plus to become H2O, becomes H3O plus. So not only has the hydrogen count increased in my subscript, but I've added a positive charge. In my acid, not only has my hydrogen count decreased, I've gone 1 to 0, but I've also lost a positive charge, and in this case, gone from 0 to negative. If you have a polyprotic acid, it loses only one proton at a time. So it actually goes to successive, what we call deprotonations, or losings of the proton. So if I have something like H2SO4, which because it has a 2 subscript right here, tells me that it could possibly lose 2 hydrogen ions, it in fact loses it in 2 steps. The first step, it loses its proton to become HSO4 minus, and then HSO4 minus could lose that additional proton to become SO4 2 minus. So Arrhenius makes it seem like they just dump them off at the same time. Bronstead Lowry says, no, that's not how it works. First, all of the H2SO4 molecules lose one of the protons, and it's only after everyone has lost their proton that we then go after that second proton that anybody has. And a Bronstead-Lowry base is going to accept that proton, and it will only accept one proton at a time. So if I have nothing but sulfate ions and they're accepting that proton, all of the sulfate ions will first get a hydrogen ion before anything can gain a second hydrogen ion, right? So it's like serving people at Thanksgiving. You want to make sure that everybody gets a bit of all of the stuff that they want to get before anybody can get second. So that second proton is your second helping. An amphoteric substance is something that can act as either an acid or a base. So HSO4 minus, or the hydrogen sulfate ion, can either lose that extra proton, thereby acting as a Bronstead-Lowry acid, or it can, because of this negative charge, actually accept another proton to become sulfuric acid again. So there are a bunch of substances that can actually act as acids or bases, and it's not like they're like, oh, well, today I feel like acting as an acid or a base. It really depends on the situation that they're in. It's harder for something that's negatively charged to lose that extra proton, so I have to really coax it off. It's much easier for it to gain a proton. So most amphoteric substances, if they're negatively charged, will act as a base, preferentially, rather than as an acid, but it could act as an acid if it wanted to.